All right, let's get started. Welcome back. Happy Friday Fun Day. We're going to try to continue that demo I was working on last Friday. We were exploring a little bit of FPGA design. We were using the Xilinx Vivado software, which is different from the Altera Corda software you're using in the labs. It's just a little bit of an easier software for me to use here as I demo, but it's doing extremely similar things. Almost a one-to-one correlation between the features in this tool and the features that will mostly be kind of automating away in Cordis as you use it for your projects. So there's a couple things to cover here. So where we left off, and we didn't get very far last Friday, was building a basic design for a particular FPGA board. The one we're using is that Nexus video FPGA board, which you can see sitting here so nicely on my desk, and I don't think this will crash our stream again when I try that this time. Uh, and there was just a little bit of setup, and we also told the tools to, hey, generate a file for us so we can get started. I know that that file in Vivado itself is a little hard to read, so I also have it open here in Studio Code. And it was very simple where we started off, right? If we were to draw out this design, and I think you should all be able to at this point in the semester. Technically, that's backwards. Technically, we should be drawing out our design first and then developing the code for it. But we just threw some very quick code together. But then now we should be able to look at that code. Or another way to think about it is we should be able to analyze someone else's code and get a good feel for what type of hardware is being elaborated on the back end. And for this one, we have a few inputs. So we have a clock, a reset input, as well as that board had those 8 switches and 8 LEDs that were next to each other. So we're just connecting those as pins on the device, as ports on our design. And we have a little bit of behavioral code that, if rising edge of the clock, set the LED outputs to the complement of the values of that switch. So if we were to draw that, I think we'd be capable of it. Let's call this design number one, because this probably isn't an interesting enough design to sustain us for the entire example, but we'll start with it. So a design one, if I were to draw this, and there's some different ways one could draw that design, even given the same understanding of what it's doing, is we recognize that there's an input switch coming in. There's a clock. We didn't actually use the reset at all. We could have reset it. There's nothing wrong with doing that, but it's also probably not super necessary. So this design one has the switches coming in, and I would just draw that as a input vector, which we called SW for switch, and it was an 8-bit value. And it's not just inverted, it's also inverting it and storing that result on the rising edge of the clock. So as we've talked about when we were building our flip-flops and building our register files, we haven't talked about it that much in class, the syntactical connections to that. But when you have that rising edge of the clock, that is inferring a flip-flop. That is inferring some synchronous state storage. So there's our clock. We could label it clock if we wanted to. And then our actual output doesn't have any other signal name. It's just we're directly mapping that to the LEDs, which is also an 8-bit signal. That would be my interpretation of what that code is doing. And what we also started to talk about last Friday is a very little bit about field programmable gate arrays. I don't know how much in the weeds I'll get in that today. I care more about the tool flow than about the device itself for our purposes. But the tool flow is significantly different than what you've been doing so far. It starts off very similar. So what I'm attempting to depict here is, we start with, I would say technically you start with your diagram, you start with your schematic, your idea, but okay, you're entering things in terms of your VHDL source or your Verilog source, and there's this loop that you've gotten pretty familiar with so far, which is you save your file, you compile your file, you execute some sort of behavioral simulation. That is model sim or any type of simulator that is model sim like, um, attempting to determine what you were trying to do with the hardware. And there's a pretty strict model it implies for what the various statements in VHDL or Verilog correspond to. And you run into all the problems of dealing with that tool. But that's the loop we've been in for quite some time, and that's a common place to be, right? You need your design to be behaviorally whatever. You need to be correct before you have to worry about going to those next steps here. And the nice thing is Vivado does allow us to do it. It's here. The flow is a little bit more complicated than just model sim, but certainly there's a step here where we can just specify on the left, run simulation for it. And specifically for this, there's other types of simulation, but the one you would start with before you move any further along would be run behavioral simulation. I'm not going to spend too much time on this because I don't think the point of it is for us to become experts in Vivado. But I would say hopefully you'll see this as a positive that you have learned model sim uh, pretty deeply this semester. I do think that's the case. Many of you have certainly, and collectively we've done a pretty good job of learning model sim. And now here's a completely different tool, but there's so much in common. They're all doing roughly the same type of things. So without even being an expert in this tool, you know, I have a clock here. I want to force that to be a clock, or I have a signal called clock. I want to force it to be a clock. Well, let's try right clicking on it, and there you have it. There's force clock, and that's slightly different. It's trying to be a little bit more detailed in terms of leading edge value, trailing edge value. But let's just give it the we don't care about duty cycle for what we're doing. Let's give it the 10 nanosecond period. Let's also set our switch, our input value here, hexadecimal value. Oh, what would be an interesting value? I don't know, 54 hex. And then we should be able to run it for a short period of time, which again is kind of hidden. There's a million little tiny options, just like ModelSim would have. We run it for a short period of time, and then I guess if we wanted to convince ourselves that this was actually um, correct, it does look correct, but maybe mapping it to binary would make it more obvious that it's doing the inverting, and it's doing it at the rising edge of the clock. This actually ran for 10 microseconds, and there's not a lot going on, right? We didn't change the switches at all. That's a lot of clock cycles, and I think we'd have to zoom in quite a bit to actually see. We'd have to zoom in quite a bit to actually see if that's the case here, and we'll do so at another time. So there we go. We should be able to zoom in. There it is. So not a lot's happening in the design. We didn't even set the reset. We're not using the reset signal, but for 381 purposes, hey, we've tested the design. We have finished that step of the design flow for our field programmable gate array. Yes, our FPGA based design here. The cool thing though is there's a lot more analysis that these tools have to do that we have to understand what to do. I'll get to synthesis in a second, but generally, and ModelSim could provide this, but it just doesn't provide it in a way that I'm familiar with. It'll actually show you if you click that feature for analysis of the RTL, what hardware it's generally trying to understand from your model. What is your behavioral model trying to do? And so this is kind of cool. I think anyway. And this should map pretty closely to what our diagram looked like. In fact, it really should be exactly the same as our diagram, right? So the design is what it is: input switch with an inverter getting mapped to a register. Here it's showing each of the the bits as this array of flip flops, and it's got the 8-bit inverter, and it's actually connecting the clock, and it's even showing you, hey, you have this reset signal, and you didn't actually connect it anywhere. That's not magic, right? Model Sim has to build something very comparable to this as well, because it has to be able to simulate what you're trying to do. And that's what this elaborated design would allow you to do. It allows you to understand from source code to a behavioral model. And the behavioral model would be things like you have something that's effectively an inverter, so you have to invert based on the standard logic function for implementation of not, and then that would be connected to a register because you're storing that at the rising edge of the clock. It's analyzing your design and giving you a behavioral model back out. The manufacturers and the software developers for this call it different things. uh, Xilinx calls it RTL analysis. That's fine. This next step here, which is run synthesis, and I'm gonna rerun it, but I'm gonna let it run and then go back and let it wait. Not taking that long, it looks like. Um, is that next step though, and this is definitely something you haven't done yet. The word itself is a very overloaded term in all sorts of design automation, but I would say a more precise term for what the tools are doing right now would be referred to as logic synthesis. You may have you may have learned a little bit about this in 281, but maybe not. Maybe this was just a little bit hidden underneath the hood, and it's still somewhat hidden. There's classes we do offer at the 400 level that talk more about the algorithms required to do this properly. Um, and it's actually, frankly, I've taken classes in those myself, but I'm not an expert in those algorithms either. It's a very active, completely separate area of research. The algorithms to go from a behavioral model for a circuit to an underlying implementation. And the idea of this synthesis just means to combine things. it's taking that model of what your hardware is supposed to be, and it's attempting to map it to what library of computing uh, gates and other things that are available on your target device. So synthesis would vary widely depending on which type of FPGA you're using. Also, if you're mapping to an ASIC for an FPGA or any other sort of hardware target, the output of that synthesis would look quite a bit different. It's going to give you something a little bit closer to a gate level view of what's happening in your design. I would guess that the problem with our current design is it's not going to look that exciting, and that's why it just took a split second. We already kind of are at a gate level design, so there's not that much for it really to synthesize. But in theory, though, you can certainly discover problems in your design at this stage, and you'd be going back to that VHDL source at that stage. And that's a new step for us, right? With regards to model sim, we were done, right? We get it to work in simulation, we're done. And now, if we're attempting to map it to actual hardware, the synthesis engine could tell us certain things about our design. It could fail. It could come out with an error, even if all your syntax is perfectly correct. You may have something that's not hardware friendly. And we talked a little bit about that, where I would tell people, well, make sure you have your sensitivity lists correct, or you're doing something that looks awfully creative and it may be a bit too creative for the synthesis engine that we're ultimately using to be able to understand that. That is definitely a painful place to be. There's no doubt. Generally, though, you'll get used to that. Just like you've gotten used to the type of model sim compiler errors and, of course, behavioral flaws that you're trying to fix, you will also get used to logic synthesis errors. Just like in model sim, certain things, certain messages it will tell you will actually be listed as warnings, but they're very clearly errors, right? That if you get this warning, your design's just not going to work and you should stop, even though it's not strictly elevated to the point of an error. Same with model sim. We've seen that a lot with model sim as well. And we can actually also simulate this post-synthesis design. I find it's not that common that people do that people are more comfortable analyzing the results of synthesis. But once you've gotten past behavioral simulation, you want to avoid doing lower level simulation because that's it's at a lower level. It's at the individual gate level versus at a behavioral level. There's that many more signals. It's that much slower. Debugging and figuring out what you want to find is that much harder as you go. I would also argue, and not that this is necessarily the recommended approach, I also see this quite a bit as well, where people kind of just skip this entire step when they know they're doing FPGA design, which is I have a design, I'm just going to run it. I'm just going to build it and run it, and that's going to be my testing. That's never recommended, right? You want to make sure you have a design that's generally what you want it to be, and then you go to those next steps. But I do see people follow that process quite a bit. Synthesis looks like it finished pretty quickly here. At least it's done for us now, and we can actually open that synthesized design. It would also report back things such as here's how many logic elements of various types are being used. Um, I should be able to see the schematic for the synthesized design is what I would want to see actually. So this is the synthesized version of it. It's going to look extremely similar by design here because our design was so trivial that it's going to look so similar. Um, one second here, having a little bit of another technology issue. Let's 1 second. Let's turn off all those messages that are coming on here. But you can take a look at what's happening in this diagram here, which is, you know, it's very similar, but it's breaking it down into individual logic gates that are going to. Let me see if I can zoom in here. That are going to correspond to the resulting device eventually. So it's not that different. It is grab the input. Here's our individual gates. Uh, Here is actually this that's not the inverter. It looks like it, but it's not. That is a input buffer to actually grab the input from the pin on the chip. This is the actual inverter now. Now it's mapping to something called a lookup table, and I don't know how much that was covered in 281. But the lookup table is the fundamental underlying computing primitive for these FPGAs. And it's a lookup table. It's a small SRAM memory. The size of it depends on the device that you're targeting. And it's storing effectively the truth table for your function. takes inputs, where the truth table tells you the ones and zeros for that function, like we've drawn out a million times. And the way these devices then are reprogrammable is because they're just little SRAM memories storing truth tables. If you want to change this from an inverter to an AND gate, all you have to do is reprogram those SRAM values, those little memories. And there's a lot of them on the chip. There are, depending on the chip, tens to hundreds of thousands of those lookup tables on that chip. And so then between them, you have relatively complex functionality you want to implement. It all gets broken down into these truth tables, and lots of algorithms are being applied to that process. And then they're all getting mapped to what's available on that particular device. That is the first part of what we call logic synthesis. And for an FPGA, for the logic synthesis, your result is going to be in terms of the built-in things that are on that device. That's a LUT1. Well, that's a one input lookup table. It's an inverter, right? There's only so many options for a one input lookup table. It's either a pass-through or an inverter. That's all you can really do, right? There's also little LEDs, or excuse me, little flip-flops that are part of that computing fabric, and it's mapping that register we saw in the behavioral model to those individual flip-flops that we have there. I neglected to mention something that's actually pretty important for this step. We have this source file that we've inputted, and I've mentioned that the entire chip is programmable, or that's what the field programmability corresponds to. You're not actually, in a field like a farmer or an agricultural context. It's post manufacture you're able to deploy different hardware to this underlying device. The chip is programmable. The board, this thing, is still pretty fixed, right? This is a pretty conventional printed circuit board. So that blue weird looking heatsink thing, that's the underlying FPGA chip. The rest of this is just a pretty conventional, multi-layer PCB here. HDMI, USB, UART, Ethernet, the LEDs and the switches and whatnot. The chip is programmable. The board has pretty fixed traces here. And so consequently, if I want to access my switches and my LEDs, as well as my clock and my reset, as well as anything on this board, I can call a signal named switch in my design and named LED in my design, but I have to constrain where that signal is actually going to correspond to on my chip, because ultimately, you can't really visually inspect it and see if that's the case. There's a trace on this board that's connecting those switches to particular pins on the FPGA. Not any arbitrary pin. It has to be, the PCB had to have been actually, designed and fabricated. It itself is not field programmable. So I did it kind of offline here. There is almost always a secondary source you have to create for your design targets for FPGAs, which is a constraints file. And that file can constrain all sorts of things about the design, but most importantly, what it generally constrains is for certain named signals you have in your design, where physically do they need to go on the FPGA chip? Because assuming you've bought a PCB and you're not separately designing your own PCB as part of this, it has to go in a particular place. It's not your call. It's not your choice where those go. Generally, the manufacturer for the board would provide you this file. It would also provide you, the 300-page data sheet where you can reverse engineer where things are going to go. But the syntax for this can be a little bit ugly. So the only example I think I'll show you here is it's saying, and it's using that tickle script just like everything else is here. Find a port named LED of bit 0 and set the property of that port that it needs to go on pin name T14 on this particular FPGA. Why T14? The engineers at Digilent put it there. There's no other answer for it than that. There's no magic to that other than that. We also can set a lot of other properties for the design as well. A very common thing you would also set would be, well, I have a port called clock in my design, but that is also generally a physical thing. Somewhere on this board, I don't know where, there's an actual clock oscillator circuit that is generating, in this case, a 100 megahertz input clock to the board, or to the FPGA specifically. We can do things on our FPGA to generate additional clocks, but as we analyze that input clock, we also have to be told and we also have to specify that is a clock. And not only is it a clock that's at that location, it's also a 100 megahertz clock. So the clock period is 10 nanoseconds that we're specifying there. And that has pretty big implications, right? We talk about the critical path, and unfortunately, the design we just synthesized is not going to have a particularly interesting critical path, right? It's not doing all. We can analyze it and we can report the timing summary and all that. It's just not going to look like much. But that's where that comes into play. That the tools will analyze the schematic that is generated both at this stage as well as at the later stage where that result is arguably more important, and it'll tell you here's all the paths discovered in the design. You told me that all the paths basically have to fit within 10 nanoseconds because we constrain the clock to 10 nanoseconds. And did you succeed or not? Did everything fit within that 10 nanosecond window? Synthesis will give you a hint if that is the case. We'll tell you that either the design may not fit because you use too many lookup tables. We're at no risk of doing that today, or too many flip flops or too many other things. But it'll certainly tell you based on our early estimate of what your critical path of design is going to be. You're either looking good or you're not looking good. And that's another reason why you would potentially have that feedback path here. Not just errors in terms of you didn't have a complete sensitivity list in your VHDL code, or you did something that's just a little weird and creative, did something a little creative, and it's just not going to work in terms of hardware. It's also potentially a failure point in that your design just isn't going to fit. It's just not going to work the way you want it to. That's tricky. If it's a sensitivity list issue, that's a 10-minute fix. If you can discover it, it's a 10-minute fix. If it's your design's too large or your design is too slow, that's a significant redesign, right? That's literally back to the drawing board when that's the case. That's, well, my critical path is too long. I have to now think of ways to partition that critical path. I have to redesign my whole circuit. I not start over, but I'm back to the whiteboard. I'm back to my diagram, and I'm trying to understand how I can make this fit for that particular device. Let's run the next step. So synthesis gives us basically this view of what's happening in the circuit. You could have simulated that as well. Implementation is just Xilinx's term for the next step. I think the more generic term for it would either be sort of physical design, or the term that you will see a lot when you read about these things is called place and route. Here you will also potentially get errors. They would no longer generally be syntactical errors at this stage. It would be errors. So, for example, if I had not specified a constraint file for my ports, it would probably give me an error at that point. It's that it'll say, I don't know where to put this IO. You didn't tell me where to put this IO. It'll either give you a warning and put them in an arbitrary location, or it'll just fail at that point. But here is certainly also where it's going to take those elements that we got at the output of synthesis and put them physically somewhere on the chip, or at least build a model in which they are placed somewhere physically on the chip. That's why it's also referred to as physical design. That's the placement stage. I have those 8 lookup tables for my 8 bits of inverter here, as well as my 8 flip flops. They now actually need to physically go somewhere on the chip. In a 3-dimensional space, they need to go somewhere. It usually gives you a 2-dimensional view of what's happening. But in this grid of logic that's available to us, put stuff somewhere. That's placement. And routing is, I have all these things. I need to wire them together. How do I route those wires on the chip? The only course that really goes into true depth of this for FPGAs would be CPRE 583. So if this seems really interesting and you want to learn more about this process and kind of do it yourself manually, just like we're doing manual assembly translation, ourselves in 381, 583 would be the course for that. You can simulate a place and routed design. In my experience, it doesn't necessarily tell you very much that you wouldn't already know from doing a post simulation, a synthesis simulation. Um, but we should be able to open the implemented design and look at the resulting device view of what's happening. I don't know how great this looks on your screen. It doesn't look very great on my screen, so it's probably not going to look that great on your screen. This is the tool's view of what is happening on that FPGA that's on that board. I don't think it's meant to be accurate from a physical layout perspective. It's still a model. If the components are this far apart, that doesn't correspond to anything physical on the resulting design. So it's still a model of what's happening, but it does give you obviously an extremely low level view of what's happening in the design. Let's see if I can zoom in a little bit and see if I can find something interesting. There's some highlighted cells here, so that was my hope or assumption that there was some interesting stuff happening here. I guess interesting being in the eye of the beholder. And I mean, there's a lot going here. Enhance. Okay. Um, I don't. That probably just looks like black nothingness on your screen because it's very faint on my screen, and now it's completely gone. Um, let's zoom in just to this region here, and let's zoom in even a little bit more. Okay, so this is actually showing the place and routed design. I'll be a bit more careful and say it's showing you a model of what the place and routed design is going to be, and it is literally in terms of the underlying individual components on the FPGA. That's why it was so small. There's hundreds of thousands of these individual little components on your FPGA device, depending on the size of your device. But it should be showing you an equivalency to what was in our synthesized design, at least. Um, it's a little hard to see, but this is our lookup table. This is one of our lookup tables. And this is the actual lookup table that is implementing one of those inverters. And somewhere you should even be able to click on it and find out what the actual lookup table values are. What was it initialized to? There should be some property called init somewhere here. I may have to click inside it. Um, yeah, it doesn't matter. It's just an inverter. It's not doing anything interesting. But in this case, it's a lookup table that is on the device. We're not really using most of those input pins. We only have one input going into this device. But that's what's getting routed here. And that's that line coming there. That's coming from an input switch, and it's getting mapped to that individual lookup table on the device. We also have our input clock that's getting routed in, and we can kind of see what's happening here, right? This is traveling through a lot of logic that it's basically circumventing. So I'm positive you can't see that at all right now. But those are little muxes, and there's an XOR gate here that's labeled as carry chain, which if you take 583, you'll see the connection back to 381 as to why FPGAs have little XOR gates hard coded in the design just for specifically for carry chains. We'll even talk a little bit about that on Monday potentially. Other muxes to kind of locally route stuff, and then finally a little flip flop at the end that is taking the clock, taking the output of our lookup table. And again, these wires aren't meant to be accurate in a three-dimensional space. There's not these diagonal wires going everywhere. Xilinx, I think, intentionally obfuscates a lot of what's happening from a routing perspective. And then the output of that needs to go eventually to an LED, and it's taking a somewhat circuitous path to eventually get to one of the output LEDs, uh, which we can find somewhere in this design is actually going to correspond to that one there. So we can click on that one, and so that's what's getting routed in the design. So when we've been talking about critical path, and I've been just kind of hand waving a lot, saying, well, we got to be careful if we want to be really precise about anything that has to do with our critical path. We have some intuition for cutting this logic in half should improve our critical path, but maybe now you can get a better feel for seeing what really happens in practice. There's a lot of abstraction in your VHDL, and then the underlying implementation, and even this is still just a model. This makes certain assumptions about temperature and things like that, and your critical path can even change based on transport delay of individual wires. But that actual physical placement and routing has a really big impact on the resulting critical path of your design, what clock frequency you'll be able to run this correctly in your design. And for that reason, while for our design it really didn't take that much time at all, again, it's a pretty simple design. It probably didn't try that hard. Synthesis can take in complex design 30 minutes, 40 minutes, but it shouldn't for the designs in this class. Place and route can take hours. Um, Usually, if it's more than 12 hours, something is very wrong in your design by and large. But as you start to use more and more of your FPGA, and it has to try that much harder to kind of get everything to fit and to try to make constraints, it can take on the order of hours and hours. Those algorithms, and I've admitted not being a true expert in those algorithms. Professor Chu would be the right person to chat with about those. They're all heuristics. They're all kind of just effort-based algorithms. There's no exact algorithms for getting the best possible layout on a device. So you'll see algorithms, and they'll have parameters such as how hard do you want to try? How many iterations do you want to try before giving up? And that can also directly influence how long it takes to get to a result. For the most part, for 381 designs, I haven't benchmarked it on the VDI boxes, but our design should go from input source to synthesize and place and route output in about an hour at most. So we do have to time accordingly. And frankly, there's a term referred to as FPGA hell when you get kind of stuck in this loop. because that loop can be so time consuming. And there's another step to this loop as well. We haven't actually tested anything at all, right? We've just gotten the tools to generate something for us. That is a bad place to be. Um, you would argue this semester this is a bad place to be, where we're stuck in this compile and simulate loop. But that's okay, I think. Where each test can take you maybe 3 minutes to set up and run and evaluate the results. This loop, if this loop is going to take you 4 hours every time you want to test something, that is a very bad place to be in life, right? In this semester, we never want to be in that place. But in later semesters, you may have to run into there. But that kind of feedback loop gets that much more time consuming. You want to really have things locked down as best as you can here, so you can hopefully minimize the amount of times you have to go back in this loop. There is one final step. It's just referred to as generating the bit stream. And there's nothing all that terribly interesting in that step. That's just a necessary step where it is generating basically the binary blob corresponding to the description of what needs to be loaded on the FPGA. We call that bit file or bit stream. The terms are used very interchangeably, or binary blob, bit file generation. That says generation. And here you're definitely no longer simulating. Um, it is not a simulation step any longer, but there's definitely a feedback here because now you're actually loading on the board and now you're going to be testing in theory. If your test works, if the code does exactly what it's supposed to be, you're done, you've moved on, life is good. But now the tricky part is when you've done everything, you've simulated everything and everything works, but it doesn't work on the board, what do you really do next? And there's a lot of approaches we can take. That is uh, the real pain point of being an FPGA engineer, right? You want to spend as much time in this mode as you can, get some intuition for what's happening down here, and hope that things are set up nicely so that they actually work at the end of the day. So generating the bit file should never take all that long because it's a one-to-one correlation of this representation of what's happening on the underlying FPGA and just the ones and zeros to be actually loaded onto the FPGA. I mentioned those lookup tables. That's the core element that we have here are just memories. In this case, on this device, there's 64-bit memories, and they're used to store the truth tables. And so that programming process for your FPGA is really just a big memory write of various locations, and it's got a little bit more complexity than that, but it's basically just updating a really large memory. Because that's what your FPGA ultimately really is a really large memory or a really large distributed memory. And that's what that process would be doing. Now, unfortunately, I haven't tested this to make sure it's going to work, but let's open the target. I should be able to find it. It's turned on, sitting next to me here. Um, that doesn't look promising. Let's not auto connect. Let's directly connect to the one we have here. That is just grand. Let's try one more time. Could be that restarting the device every so often kind of messes this up. Normally this works okay, but I didn't test it before coming in today. Any questions about this while I struggle to get things kind of, looks like it's going to be fine. Any questions before I show the first demo of this actually working? Lots of humor today, which I appreciate as always. I'm not going to click that link that's there. So I'm just connecting to the device. It refers to it as a hardware server. That's a Vivado specific thing. It's just a USB driver right now, like anything else. I'm going to tell it to program that device with the bit file that got generated, the binary blob that got generated. And it shouldn't take that long. It is a relatively large file, so it takes a little while to actually program here. And so we have our new design that's now running on that device. That's a lot of setup for a relatively small payoff here. But yes, that's our design, right? It takes samples the values of the switches and inverts them and then connects them to the LEDs that are on the screen that you can see there. If you humor me for a second, we can just very quickly test that things are working. I'm pretty confident they will be. That would be hilarious. And it looks like it's working, right? So we have our LED, our switches. I just kind of tweaked a few of the switches and knocked over the camera and everything, but it does look like it's working. So our inverter is working as it should be. We have plenty of time here. Let's try a design number two. What would be a nice design would be one that maybe does, this is a 281 type of design, I guess, that instead of just inverting, perhaps it does some sort of up counter, right? That takes the value of, I don't know if we even need the switches at all for this, that design them, but perhaps it instantiates an adder and connects that output to LED and gives us a nice kind of binary counter type of design, right? Where I, in designing this, I would actually start with the adder as the first component here, and it'd be maybe just a +1 adder, and takes that value and actually just does an up counter. And there you would definitely want a reset line for this to work properly, and then connects that results to the LEDs. That'll give us a nice kind of little, blinking pattern on our LEDs. This is something that you're not really required to do this semester. You can't see what I have open here. You It's not something you'd be required to do this semester. But I think if I said build a design that implements an up counter and stores the results as LEDs, I think you have the tool set to do that now. Yeah, learning how to use Vivado or Quartus better would be a necessary prerequisite, and I wouldn't ask you to do that without that training, in advance. But in terms of the VHDL, that little kind of wonky looking design with a reset on a register and a +1 up counter connected to LEDs, you should be able to do it. That's an expectation. It's definitely a valid question as we go and we edit the code here for this, which was, are you expected to use FPGAs this semester? Starting next week, we will be synthesizing our designs for FPGAs. We won't actually be physically connecting them to any of the FPGAs that are in the 2050 Cougar lab. We could have, but I think it's sufficiently interesting to be able to just synthesize the design, get some results back regarding the critical path for the design. But the takeaway is still pretty important, though. Um, we're not adding that entire loop, but we're now adding for this class that secondary feedback loop of VHDL, not just getting it behaviorally to work, but also getting the synthesis to work. And we're automating a lot of that for you. It'll be just kind of clicking a script and it should get started and work for you. But it'll be interesting, I think, because we'll start to really be able to explore those trade-offs of, group 23 implemented the shifter this way and group 24 did it completely differently. Let's take a look at how many logic resources each group wound up using. They should be similar, but the differences I think will be interesting. Likewise, what's the critical path? What clock frequency was group 23 able to achieve versus group 24? That's as far as we're going to go with that, but we are going to go to that next step starting next week in the lab. But my other takeaway I think is pretty important, that you only want to even start to even get anywhere close to sniffing this step when you're pretty feeling very good about this step, which is, I know my code's correct. Now let's analyze it from a hardware resource utilization perspective, from a critical path perspective. So there's our second design. Again, I think it's fair to say that's something I would expect us to be able to do as a class. I do. Um, the nice thing, and we've talked about that a little bit, if you want to do addition in your design, and if you use that IEEE numeric standard library, which even Xilinx auto-generated that for us, recognizing that it's an important thing, we have that available for us. We could also then create a signal to keep track of, I don't know, call it adder, to keep track of the added result. And likewise for our process here, everyone can see that, okay, right? Yeah, and likewise for our process here, um, instead of just setting the LEDs to be not the switch, what we would be doing instead would be having perhaps an asynchronous reset. So if reset equals 1, we'd want to reset that output of the register. else if, now we're back to, so actually I did that arguably backwards. So if we have an asynchronous reset, we would put that first. So if reset equals 1, then there's our adder. Else if the rising edge of clock is 1. Either way is fine. It doesn't, and if you look at the documentation for the design tools that we're using here, it's not really that clear, at all, whether you should use asynchronous versus synchronous reset. So if we have a rising edge of clock, well, we should take the result of that adder getting a +1. Not quite done. That is part of that circuit. That would be this component of the circuit. We would then also want to take the output of the adder and connect that to our LEDs. That doesn't need then to be inside the process itself. That's just kind of a signal or a wire relabeling, right? So we have LED, and we actually can't grab the whole value of the adder. That one's an unsigned. Our LEDs are actually standard logic vectors, so we would just use that little conversion wrapper function. Coding live is never a good idea for VHDL because that turnaround time can be pretty painful. But this should be okay. We're not using a lot of the signals here, but we have a reset flip-flop. We then just are inferring an adder at the rising edge of that flip-flop. And then we're taking, in this case, the least significant byte of that +1 adder and storing it to our 8 bits of LED. Let's see if, let's close out of this view. Let's see if the tools even recognize that I changed the file. No, reload. Okay, so actually, I was smart enough to figure out. So the code is there. I should probably just quickly check that it synthesizes first. It'll let me know if I added something that's going to cause it problems. It's running synth design. This will take a little bit longer now because it's at least doing a little bit more than it was before. It's at least inferring an adder, and we can take a look at what it does when we ask it to infer an adder. Any other questions about this while I wait for this to finish here? We're definitely gearing up for a bit of a change with how you're interfacing with the labs, and that'll be starting next week, where we're giving you a lot of sort of the wrapper code for your entire processor design. Not because we don't want you to be creative, but because we have something of an automated test framework. And in order to use that, everyone's code, at least at the top level, has to look kind of the same. And I'll separately create a video with regard to how to use that framework. It's relatively straightforward, but you'll have both sort of architecture questions, you'll have VHDL questions, and now you may wind up having some framework questions as well. And you will, in theory, be able to run it on your own machines, but the VDI is still probably the right way to do it. That doesn't look. Reload. Okay, I was gonna say that did not look correct. That was the previous. Okay, there we go. So now it's at least doing something a little bit more interesting than the previous one that we had here. I got the clock, got the reset, got the flip flops here. Trying to find out where the actual adder is being implemented. It is really subtle to me. I don't really see it at all. Is this the entire design, or is there more to the design than this? It wouldn't be that component. Adder reg. That so there must already be a component that's basically implementing a 4-bit adder built into the FPGA. I bet I can double click on. Let's see. Nope, can't seem to drill down into that. That's a built-in primitive to do 4-bit addition. If we get a chance, we'll talk about carry look-ahead adders that basically try to do 4-bit addition all in one go, and that's very likely what's being implemented. So that's 4 bits of the addition. I don't know if you can see that, but that's a 4-bit adder. It's not magic, right? I don't know. Carry in, carry out, data out, sum. There's the other 4 bits of addition here. I wouldn't have named it that, but this is Xilinx's tool. This is their way of doing things. You may ask, well, we did specifically specify a 32-bit adder, right? Adder is a 32-bit signal. I just happen to specify it as such. But when we look at the resulting schematic that gets generated here, it's only giving us an 8-bit adder. We've talked a little bit about this because ModelSim, even in the behavioral model generation, is doing a little bit of this. But Vivado, any FPGA synthesis tool, is going to be extremely aggressive in this, which is, you can call it dead code elimination. It's also referred to sort of an observability analysis. It's if that signal that you're using is never going to be seen anywhere, if it doesn't correspond to a physical thing in the real world or any output pin, basically, get rid of it. And so what you actually have here is a design in which I specify a 32-bit addition, but because I'm explicitly only ever using those lower 8 bits of that adder signal that I've used here, the tools, and we could probably find a million messages that specify this, but it would take me a while to hunt them down, is going to aggressively just trim the rest of those signals. So I specified a 32-bit adder. It was smart enough to tell me, well, you didn't need a 32-bit adder. You actually only need an 8-bit adder, and I'm only going to provide you with an 8-bit adder. To me, that's a very good thing. That allows our design from the VHDL perspective, as long as we're aware that it's happening, it allows our design from the VHDL perspective to be very clean and straightforward and simple. And if we already built a 32-bit circuit that we like, let the tools optimize the stuff out that we're not using. So for example, in your processor project part B, where you have to calculate PC equals PC plus 4, you may be tempted to create a separate plus 4 circuit, but you don't need to. Just use your adder, just use your ALU and hard code it to be plus 4. The tools will figure out the rest. The synthesis tools certainly will figure out the rest and will determine what parts of that logic are actually needed for that plus 4 operation, and let's remove the rest of it. And there's quite a bit you can get rid of when you know it's adding a constant. And if you're not using all of your bits of representation, it can remove all of those as well. We seem to have passed synthesis, so in the time we have remaining, let me just attempt to generate the bit stream for this design here. It does not, okay, so it is now doing the place and route. It'll look a little bit different because it's got more stuff going on, but not really um, all that more going on. Um, so there's an interesting question about, what does it mean to be an FPGA? Uh, FPGAs are very good for certain purposes. Uh, they allow you to, as we're about to show here, change what hardware is running on this platform basically as many times as I want, whenever I feel like it. So it's upgradable, right? If there was a serious flaw in my hardware and I wanted to change it a day later, a month later, a year later, I can do so. It comes with a severe cost associated with that. If we look back to the inverter example, where we took the switches and we're inverting it to get the LED outputs, that inverter was implemented as a lookup table, which is cool, right? We can implement any logic function as a lookup table. And that lookup table is directly instantiated on the device. We built an SRAM memory to implement that lookup table. That's programmable. That is a cool feature. It's going to be extremely slower than actually mapping an inverter using CMOS technology or just low-level gate layout technology of any type. It's a huge overhead. In the case of the inverter, each bit of SRAM storage is roughly 6 transistors, and you have to use a whole 6 input LUT for it. It's a several hundred order of magnitude, not necessarily slower, but larger implementation of that inverter. Versus if I knew I only wanted a chip that inverted switches and generated an output, or did any fixed function and never was going to change, you could build it with significantly fewer transistors. It'd be significantly faster, it'd be significantly smaller and more better in terms of power consumption. So we use FPGAs when we know we don't necessarily need bleeding edge speed. This is running at 100 megahertz. You can get certain designs up to 300 megahertz. You almost never see anything faster than that for an FPGA design. And it's great as a teaching tool as well, right? Or as a research tool. I can't afford to fabricate chips. We can't afford to do that for this class, right? If you take the VLSI sequence, you get a little bit of an experience in doing that potentially. But for this class, we want to test 500 designs quickly. We don't want to build a design, wait for 6 weeks, get our chip back, and test that. So FPGAs are wonderful for that purpose. And they're used. They're a legitimate product that is used all over the place in terms of networking equipment, on your motherboard. Glue logic is a very common place. You will see them used for that purpose, controller logic. But there's a pretty extreme trade-off involved in terms of the resulting performance of what that design can do. Stick with me for just one more moment here because we do have the design did get generated. Let's open our target again. I don't know why that didn't work a second ago, but it was working now. And let's download that new bit file onto the design. Okay, taking just a while to go. I don't know why it's taking so long. Maybe I'm not normally just waiting for people for it to run. We're going to program that next bit file corresponding to that +1 design. And is it going to work for us? Well, let's find out. What do we see? Is it counting? You could probably maybe necessarily see it. So the answer is no. And as an open question, people asked about, do we get credit for showing up to class and things like that? You do. You get credit because you're learning so much as we're live here. This design, kind of sort of by intention, and again, I'm referring to if you want to look at the logic for it, this design of that +1 circuit is not toggling the LEDs as far as we can tell. I'd like you to think about it if you have some time over the weekend and post on general. And I'll give credit to the first person who posts what I think is the correct answer. I don't know how much credit. You guys don't need credit. If you're thinking about this and working on this, you're the student who doesn't need the credit for this class. Um, why we think that's happening. What did we, I'm not going to say I, because I didn't intentionally, what did we collectively do wrong as we designed this circuit? And let's see if we can figure out what a workaround for that solution would be. And I'd be happy to implement that workaround along the weekend before Monday and show what that workaround would look like. Otherwise, I think we're at time. Let's leave things here for today. Um, Looking forward to seeing the completed project part A and really moving on to that next phase of the semester. Otherwise, enjoy your weekend. Thanks.